we have just had the best introductions that could be by Professor Seeger. And I'll talk about the extended habitable zone of red dwarf stars, which has to do somewhat with the climate of exoplanets. If exoclimate is okay, what about Earth's climate? And we just on Saturday, they came out on a Ynet, which is the greatest news port in Israel, an interview with me about the climate problem. Well, I am no climate scientist, but I did have some very definitive opinions, and that investigator from the Hebrew University, that's me. And on this single interview, I got by far more reactions than any of my other astrophysical interviews. So this is a very loaded subject, but we'll go over to our subject, which is why are red dwarfs so interesting? Sarah already said some of the stuff, so I can pass very fast. One thing which didn't say is the demography. M stars are about 75% of all stars. And then exoplanets of M star are easier to detect, that she already said. Why? Because red dwarfs are faint. So their habitable zones are smaller, and habitable planets of red dwarfs therefore have shorter periods. Now this makes them easier to detect, because to detect by a transit or by Doppler method, you need at least a few orbits. And if each orbit lasts 1 or 2 Earth years, your mission is over before you detected it. And there is another, this is actually the reason that Sarah emphasized, larger transit dimming. The ratio between the radii, as she said, Earth-Sun is the surfaces area, 1 to 10,000. Earth to a small red dwarf is about 100 times larger. And this becomes crucial when you are studying the biosignature of an atmosphere, which is for Earth, for example, it's only less than 1/3% of the whole area of Earth. But let's look at the habitable zones of red dwarf stars. And here we have, for example, a Kepler 62. The green area is a habitable zone. I'll get a little more detail what is exactly the habitable zone. Roughly, it's the area which allows liquid water on the surface of a planet, of course, with a suitable atmosphere. And we can see that the habitable zone of the red dwarf is much smaller than that one of the solar system. And there is another thing, habitable planets, that is planets within the habitable zone of M stars, of red dwarfs, are locked. So in this somewhat complex diagram, you see the distance in astronomical units from the parent star, and the type of the star, of the parent star. Astronomers use these letters to indicate stellar types, but here we indicate them by masses. So here, for example, 1 is our solar system, and we have here all the planets of solar system. Mercury is within this dotted area, and the yellow area is the habitable zone, which varies. The distance varies because of course, the heavier the parent star, the brighter it is. And if we look at the area which is tidally locked, it means the place which, like Mercury, shows only one face, the same face to its sun all the time. This is very interesting for the climate and for the possibilities of life. And we can conclude from this diagram, for example, that M stars, red dwarfs, habitable planets of M dwarfs are most of the time locked, or almost always locked. So let's switch to a side subject, which is the surface temperature of a planet, or planetary climate 101. So this is the basics. And if we study basic astrophysics, we learn that equating the incoming stellar flux to the flux radiated by the planet, these two, gives us a simple relation between the stellar and planetary surface temperature. So we have to use this basic relation for the luminosity of the parent star, and we get this equation, which says that the stellar temperature divided by the ratio between the stellar radius and the distance of the planet from the star, the square root of this gives you the planetary temperature. So this is true for locked planets that show all this only for their day side, of course, the side that is turned to the sun. For rapidly spinning planets like Earth or isothermal ones like Venus, one gets another factor of 2, but basically the same relation. And now we should learn a little about greenhouse factor, or how heat forcing causes global warming on exoplanets. On Earth, we already know it. So CO2 or other greenhouse atmosphere acts like a blanket, and it's impeding our heat radiation from the planet. So to this outflux, we had another factor, which is the heating factor, which is usually bigger than 1. For example, Earth has a heating factor of 1.7, Venus it's about 40, and this gives us the equation for the planetary temperature like this, or the other case like this with another factor of 2. And now about biohabitability. This is related to the habitable zone. The definition of the habitable zone, as we said, surface temperature allowing liquid water. And I introduced this item, or this idea of biohabitable zone, the surface temperature allowing liquid water and complex organic molecules on at least part of the planetary surface. And this becomes extremely relevant for locked planets. So the biohabitable temperature range can be defined approximately between 0 Celsius, which allows liquid water, and about 130 Celsius, which allows complex organics, like we have in the bottom of the sea. Above these temperatures, this very delicate organics, as we know it at least, begin to disintegrate. So naive boundaries of the habitable zone would be the outer boundary, which is about 0 Celsius. And here we reversed these equations that we have for the temperature, and this expression here, note the heating factor. And the inner boundary would be about 130 temperature, surface temperature, which would give you about this relation. 400 K is about 130 Celsius. And we can, this is naive because this does not take into account really, in a real sense, the atmosphere. This is in locked planets, however, the picture is more complex. There are huge temperature differences between day and night sides, like in Mercury, for example, it's approximately between minus 200 Celsius at the night side to above 400 in the day side. The implication for red dwarfs is that significantly broader habitable zone boundaries. Biohabitable temperature range from, for locked planets, in the minimum, the night side temperature should be lower than about 130 Celsius, as we said before. Note that this is a little counterintuitive, but if you think about it, you'll find this is right. So to enable complex organics, and the maximum temperature, the substellar points should be larger than 0. Otherwise, the rest of the star will be frozen, of course, to enable liquid water. And here we can get a figure about how would the temperature distribution on the surface of Proxima Centaurus be, our nearest exoplanet. And it also happened to be, Proxima Centaurus happens to be a red dwarf, and Proxima Cen B is probably locked. So here we have the temperature, and we have to introduce two factors. One is the latitude. So 0 is a substellar latitude, and 180 would be the opposite latitude, which is, so this would be the day side, and this would be the night side. And the other factor that we introduce is the heat redistribution factor, or heat transport. And F is when this is total, all the heat is redistributed. Like if Mercury had an atmosphere like Venus, it would be isothermal. So it would have the temperature about like so in kelvins. But if it's not, if it has no atmosphere, like F is 0 or almost 0, like we know it is, then we have a temperature that is very hot. It's not as hot as Mercury, of course, because the sun is a very faint red dwarf, but relatively hot, of some 150 K. And then it's a transition from day to night side. It goes to about very low temperature, 0 Kelvin, ideally, but if there is some heat transport between some atmosphere, then you have intermediate cases. Let's go. This is the surface temperature range versus heating factor, H, for several cases. So this is T max and T min, and this is Mercury, Earth, and Venus in our solar system. Of course, these 3 planets are on the equilibrium curve. Mercury, however, has a range of temperatures. And this is a temperature for locked planets. I'll have to make it a little faster. So here we have a transition taking into account atmosphere. That's a numerical simulation show this. Here is the water regime, liquid water regime. Here A is the albedo, eta is the heating factor, F over Fe is the stellar flux relative to Earth. Here we have Venus, it's much beyond, but for H equal 10, we are already, the night side will be within the liquid water regime. Earth is about here. So we see if Earth would be locked, we'll have a region in the middle around the equator, which would be, and so on. So minimum and maximum heating factor for locked planets. Of course, we have the hottest point is a substellar day point, and we want there to be at least 0. And the opposite, the antipode of that, would have at least 130 degrees. If it would be hotter than this, the rest of the planet would be much hotter. So for a planet to be habitable or biohabitable, we require that T day will be larger than 0 and T night smaller than 130, which give us a heating factor, a constraint on the heating factor in terms of the redistribution or transport factor. And here are a few figures which I don't have time to study them a long time, but only here we have the distance in AU from the red dwarf, and here it's for a very dim red dwarf, 10 to the minus 4 solar luminosities, and we see between these are the maximum lines, temperature, this is the maximum greenhouse factor H, and this is the minimum, and we can also draw this in a logarithmic way, and then it all comes much nicer. For example, Proxima, this is Earth's flux relative to Earth. Proxima B would be about here, and so on. And these are the 2 planets which we published the paper with Talor. Now let's get to the final diagrams. I guess I have about more 10 minutes, if I'm right. Hopefully, well, I'm the chairman, but I don't calculate for myself. So these diagrams are fairly well known, and they should be given a very good credit because they show us the habitable zone, this green area, in terms of the stellar flux relative to Earth. For example, this is a flux that Earth gets from the sun for different stellar types. And these types are sorted here. These are the astronomical letters. M stars are here. And the temperature, surface temperature of the suns are here. So our sun is about 5,800 Kelvin. And surely enough, here is Earth. Earth is well within the green area. But if our sun would be of a similar luminosity, but in the wavelengths of red dwarfs, in the infrared mainly, then Earth would be out of the habitable zone. And this is because it is dependent also on the wavelengths of the sun. That is, and here we have an interesting thing. Here we have Venus. We see Venus is outside the habitable zone. Here we have a zone that is between the runaway greenhouse effect, which I will not explain because I don't have time. And so this area here, there may still be habitable. It depends on the climate and so on. And here we have the cold region, and look at the boundaries. Maximum greenhouse here means the planet with the densest atmosphere, carbon dioxide, that can heat up the planet and cause it to be still liquid water. Early Mars means that Mars in the early time, when Mars was really young, and we have signs that we had liquid water on Mars. So this is a diagram of early Mars, if we believe in this line. And recent Venus, this is a theory that Venus until recently was habitable, and now it is definitely not, but this means that we have this optimistic line here. Okay, Proxima B, for example, would be here. Most of the exoplanets, Earth-sized exoplanets discovered are of M dwarfs. Here we have a similar diagram. Again, recent Venus, early Mars, etc. And here we have a comparison with 3D simulations, which shows exactly what I got on a theoretical argument a few slides ago. So we have, for rapidly rotated planets, we have this line here. So this is 1D, inner and outer boundaries of the habitable zone. And for models, we have for rapidly rotating, this is a boundary, the inner boundary, and for inner slowly rotating and tidally locked planets, we have this line. And here there are numerical results, this axis, and it's amazingly, this is very well agrees with my theoretical evaluation. Here, by the way, is a tidal locking radius, and we see most of the candidates for exoplanets of M stars are within the tidal locking regime. So conclusions, very fast. I can tell you that planets of red dwarfs, RDPs, may be found within an extended habitable zone due to gravitational locking. Liquid water can exist on RDPs for a wide range of atmospheric properties, for example, greenhouse heating, heat transport, etc. Conditions on RDPs may be suitable for Earth-like organics and life even within a limited latitude or belt of latitude. And finally, stay tuned. In the near future, James Webb Space Telescope may find evidence for life on transiting habitable RDPs, red dwarf planets, and Sarah may be the one. Thank you.
Amri, you did wonderfully. You stopped exactly 5 minutes before the end. So you have time for questions. How close to us is one of the better in the choice?
I need you to repeat the question. I didn't get it.
I mean, how far in light years is one of those nice stars that we might wish to visit?
Oh, of course. The closest one, Proxima b, is just 4 light years, just our doorstep. And typically, those are some few tenths of light years.
Well, most of what we see, what the catalog is usually until what, about 100 light years?
Yeah, even more. There are some examples even more. But for example, the planet on which one discovered the 1.5 years ago, water vapor, by the same method that James Webb would probably need to discover life signature. This is called K218b. This is 110 light years.
Well, that's about 100. So I know it's really stupid, but is there any chance to get closer, to fly there?
Oh, to get closer to the planet.
Maybe Elon Musk can do that.
Yeah, I think even Elon Musk no, but there have been this initiative of breakthrough starshot, which says they can fly a tiny camera, a nano camera, within 20 years. This is still a very long way to go. The idea is nice, but to evaluate it, one would need a lot of money and very, very many more breakthroughs in technology. So if there are no questions, of course, it's no harm of saving a few minutes, but I want to share with you one thing that excites me very much in the last weeks. In about 1 month, they'll come out in press the first astrobiology textbook in Hebrew in the world. And this is a book that I've been designing for a long time, that goes along my course. And indeed, the dream is realizing now, and soon enough, I hope you could, if it would be a physical conference, I could hand out to you some copies.